For this section, we're going to be talking about inverse functions. So we're going to start off by defining what an inverse function is. We say f and g are inverse functions if fog of x is equal to x and gof of x is equal to x. Meaning, remember this notation means f of g of x. We're plugging the function g into the function f. And here we're plugging the function f into the function g. It works right to left in both cases. Okay, so we're saying that when you plug each of the functions into one another, the result always just has to be x. And if that is the case for both of them, then they are inverses, and we write that as g equals f inverse. It could also be written as f equals g inverse. Both would be true. And it is also very important to note that this notation, f inverse, f with a -1 that looks like it's its exponent, does not mean 1 over f. This -1 does not represent an exponent. It is just a notation. It's very odd. It's almost as if we ran out of notations in mathematics, but it is very important to note you cannot treat this as an exponent. It is just a symbol to represent the inverse function. Okay, so with that, we have an example that says we want to check if g and f are inverses or inverse functions. So we have f of x equals 5x and g of x equals x over 5. So to prove that these are inverse functions or they are not inverse functions, we have to find fog and gof. And when we find them, the result has to be equal to x in both cases. So starting with fog, we're finding f of g of x, which means we're plugging g of x into f of x. So when we plug g of x in, we know that g of x is equal to x over 5. So we're plugging x over 5 in everywhere we see an x in our function f. So function f is 5 times x, which means it's now 5 times x over 5. Again, we have just replaced this x with what's in parentheses here, x over 5. And when we do that, 5 times x over 5, the 5's will cancel out. If that confuses you, remember you can always rewrite a whole number as that number over 1. And now when you're multiplying two fractions together, if you have a common factor multiplied in the top and the bottom, you can just cancel each of those factors out, which just leaves us with x over 1 or just x. So fog f of g of x is equal to x. That checks out. Now we have to prove that gof is equal to x. So gof g of f of x is taking the function g and plugging f into it. And we know f of x is equal to 5x, so we're plugging 5x in to the function g. When we plug 5x in, we get x over 5 is now going to become 5x over 5. And we can cancel the 5 from the numerator and denominator, which leaves us with just x, which means gof is also equal to x. And since fog and gof are both equal to x, then we can say g is equal to f inverse. I wrote a little too big here. I apologize that this looks a little messy. But again, they are inverse functions because fog and goff, what we got when we plug each function into the other function is x. So g is equal to f inverse, or f is equal to g inverse. From here, we can now introduce this process that says to find an inverse function, we're going to replace f of x with y. So when you start with an equation, or a function that is, and you want to see its inverse function, meaning it's not given to you, you're going to take the function notation, which is usually f of x or g of x or h of x, and replace it with a y. You will then swap all of your x's and your y. So your y will become an x, your x's will all become y's, and then you will solve for y alone. A note, if you cannot write y alone, not meaning you can't do it, but meaning it literally cannot be done. If it cannot be written alone, then the inverse function does not exist. But if you are able to write y alone is equal to something just involving x's, then that means you have found your inverse function, and you can now replace y with f inverse of x. So let's go ahead and try that for this example. We want to find the inverse given f of x equals 3x minus 4. The first thing we're going to do is replace f of x with y. So we have y equals 3x minus 4. We will now swap all x's and y's. So we get x equals 3y minus 4. And now we're going to solve to get y alone. So we will add 4 to each side, which gives us 3y equals x plus 4. You could also write this as x plus 4 equals 3y, but typically you want to leave your y on the left side of the equation. And now from here we will divide each side by 3 to get y equals x plus 4 over 3. Notice y is completely alone. There is only one y, and it is equal to only x's and constants. That means we have gotten y alone. We have found the inverse function. We now replace y with f inverse of x, which is equal to x plus 4 all over 3. And one nice thing about these problems is you can always check to make sure you have the right answer by simply taking the original function and plugging the inverse into it. The result should equal x if you've done this correctly. And then take the original function and plug it into the inverse, and again the result should equal x. That's what we were just doing over here with f and g. Continuing on from here, we now want to find the inverse given f of x equals x squared. So again, going through this, we're going to swap f of x with y to get y equals x squared. We will then swap x and y to get x equals y squared. And now to get y alone, we're going to have to take the square root of each side of the equation. Apply the square root function to each side, which gives us y equals plus or minus the square root of x. But notice there's an issue here. What happens if we let x equal 1? Then we would get y equals plus or minus the square root of 1. The square root of 1 is just 1, so we would get plus or minus 1 which gives us the points x equals 1, y equals 1, and x equals 1, y equals negative 1. Notice that we just repeated our x value with different y values. That means this is not a function. If it's not a function, it cannot be an inverse function, meaning the inverse does not exist. So this is always something to look out for. If you get multiple y values for the same x value, the function isn't possible. So there is no inverse function. But that's not always easy to prove, so we introduce the horizontal line test, which says that if any horizontal line intersects the graph at more than one point, then the graph has no inverse function. It's similar to the vertical line test, which said if a vertical line intersects the graph at more than one point, then the graph is not a function, that is. So horizontal determines if it has an inverse, vertical determines if it's a function. So looking at these two examples, are these functions that have inverse functions? Well, in the first example, if we take this horizontal line, we can see it intersects at 3 points. That means it instantly fails, so the inverse does not exist. Now take a moment, see if you can decide whether this function has an inverse. Okay, so trying this together, hopefully you notice that if you take this horizontal line, or any of these horizontal lines except at the very bottom, they will always intersect at 2 points, which means this graph also does not have an inverse function. Continuing on from here, there are some exceptions though. The following example will show that. If we were to go through this problem, then starting off with our process, we would have y equals x squared plus 2x plus 1. And at this point, if we tried to swap the x's and y's, so x equals y squared plus 2y plus 1, we wouldn't have a way to solve for this just getting one y. It wouldn't be possible to just get one y out of this very, very well, that is. The only way that we could do it is by introducing factoring into the problem. So if we were to take this problem, what we originally started with, so let me erase this back to here. If we were to take this problem and factor it, which would give us x plus 1 times x plus 1, then we would have y equals x plus 1 squared, quantity squared. Now notice that when we swap x and y, we get x equals y plus 1, quantity squared. We now have a way to get this y into just one y. Technically there are two of them. Y squared will end up being two different y's, but in terms of what we're looking at, we now have just one y term instead of the two y terms we had before, the y squared and the plus 2y. There still is an issue with this though. When we take the square root of each side, as we did in that previous problem, we would end up with y plus 1 equals plus or minus the square root of x. But there's a nice catch to this problem. The domain, right up here, x is greater than 0. Because x is greater than 0, then what happens when we take the square root of x? Well, we had the possibility of a positive and negative answer because of that square there. But we don't have to worry about that positive or negative answer because we know there was only a positive answer. Because this equation, y plus 1 quantity squared, was just equal to x, then that means it had to be equal to a positive value. No matter what happens, x would only be positive. So when you take the square root of each side, there is no chance of having a positive and a negative answer, because x had to only be positive. Another way to look at this, if you look at this graph, x squared plus 2x plus 1, if you were to graph this, you would end up getting a graph that looks like this. And now, what does the graph look like if we set x as greater than 0? Well, if we set x to be just greater than 0, then that means we only care about this point of the graph on the y-intercept moving to the right. So all of this part of the graph disappears because we've restricted our domain. So what does the graph really look like? It just looks like this, an open dot and then moving to the right, curved upward. Does this pass the horizontal line test? Yes, it only ever intersects the graph at one point. So the inverse will exist because we only have the positive x answer to deal with. We don't have to worry about this negative answer. So that means y plus 1 is equal to just the positive square root of x, and when we subtract 1 from each side, we get y equals the square root of x minus 1. We have only one y for each x. We're not repeating x values, that is. So f inverse of x is equal to the square root of x minus 1. It's always very important to try to graph these whenever you can to get a proof that it passes the horizontal line test. And this graph, we knew that if we factored it, it would end up becoming x plus 1 quantity squared, like we have here. And remember, this just represents a horizontal shift to the left of a parabola, which is how I got that general shape we had of that U. Okay, so this is one of the more complicated types of inverse problems we would end up dealing with. In general, it's usually just linear functions that you would worry about when you're dealing with inverse functions at this level. Okay, but from there, let's quickly talk about what an inverse looks like on a graph. So we say that the graphs of f and f inverse are reflections about the line y equals x. Essentially saying, given the point a comma b on the graph of f, then b comma a would be on the graph of f inverse. You swap the x's and y values, just like we were doing in those equations, to get the point on the inverse function. And vice versa. If something is on the graph of f inverse, the point b comma a, it will become the point a comma b on the original function. So on a graph, we say that if you draw the line y equals x, which I've drawn with this dotted line, and then you were to draw some function, so I've drawn this function f in black. If you were to reflect this, meaning if the line y equals x acted as a mirror, If you reflected this graph over this line y equals x, you'd end up with something that looks like this graph in red, which is f inverse. So if this is the point a comma b on the graph of f, now that x value of a now becomes the y value a. So this distance on the x-axis now becomes the distance on the y-axis. And the y value b, which was here, now becomes the x value a. The x value b, which is now here. So we are swapping the x and y values, or reflecting over the line y equals x, to create these inverse graphs.